Well, so you've struggled a little bit with protein synthesis and possibly mutations. This short presentation here will help you hopefully with how to set these up and possibly, so when you go back and redo your forms, you'll have a better understanding of how to complete, or I should say, answer problems related to protein synthesis and mutations. So let's take a look at what we need to understand. You probably saw on the form a problem that looks like this up on the upper left-hand part of the screen. If I give you a DNA strand, this comes right from the form that was about a protein synthesis from DNA. And a lot of you, excuse me, when you did this, you did not, you either gave me RNA or you didn't give the actual amino acids. So I'm going to show you what you should have answered in these particular problems by showing you what you should have done when you had this one. So in the upper question here says if DNA is CTA, TTA, and so forth, what is the amino acid sequence for the coding region? Okay, the very first thing is we have to find the coding region, and that is where you start to code for an amino acid known as methionine. And in order to find that, we have to do our RNA, and we have to draw our RNA down here or transcribe that first and then translate that into our amino acid. So let's get our pen going here, and we see here our RNA for our first one. Okay, so we know CTA is going to give you a G, A, U, and then we have TTA, and we know that T with RNA is going to partner up with adenine, and so we have A, and remember uracil is only found in RNA, and that's what A partners up with, so AAU, and then we have GCU, and then we have AUG, and we have AUC, and we have UCG, and we have CUU. And we'll finish it out here. We then have T goes to A, U, C, and then we have C, 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 G, A, and U, A, G. Now, who knows? Mr. Petit may have put a mutation in there, but hopefully I transcribed that correctly to the RNA. So we have to find our start codon, which is the methionine. And in order to find that, methionine is coded for, looks like right here, we're looking for something that would code AUG. So I see here, there's my AUG, so I know that this is my start codon right here. So this particular codon is the start codon, and that's going to transcribe for methionine, and you can just abbreviate these with MET, and I usually kind of know that my amino acid then is a particular little amino acid, and that's going to be attached to the next one. So our next one would be AUC, and we use our amino acid wheel up here. AUC is ILE. So there's your next one, and your next one, UCG. UCG is serine. SER, and then we have CUU. So CUU, we have leucine, and AUC. AUC is another ILE, and then we have CCC, which is proline, and then GAA. GAA is glutamine, and then UAG, and it looks like that one there is your stop codon, which is TER there. So we've stopped in that case there, so that would be a stop codon, and so then the protein would be cut off. So your protein would consist of these amino acids right here. And so the TER must mean terminate in this case here. For this, I know we have different amino acid wheels in this one. TER must mean terminate or stop. So this is your protein for that particular strand that is up here. And that's how you go about completing something like that. So I did this particular problem right here just to show you how to complete that. And so when you answer, your answer should have been this particular sequence that goes into this answer right here, this MET, and then you have your ILE and so forth. So you would have written that all down and just continued that basically from this section here. So that is transcription and translation of a protein, and that's how you complete that particular problem there. The next particular problem is mutation. So I'm going to show you how to solve a mutation type problem. And let's do a substitution mutation. I took the same DNA strand that we have here. And if I go back, I know that start codon is the AUG codon right there. AUG, yes, there we go, which is that TAC1. So I know that my start codon is right here. And then down here, let's say that something happened, like during replication, that a particular base or something was inserted and it wasn't guanine. So let's say that instead it was let's go with a TC. Okay, so now we have a new particular base that's been inserted here. And so what would the RNA be? So the RNA would be, let me see, we go A goes to U, T goes to A, and C goes to G. And so we look at that. Now that is UAG, and so UAG is a stop codon. So that would stop or terminate the protein right there. And so this particular mutation of a substitution, then again, this is the base that's being substituted right here. That base would cause an amino acid not to be produced and would create a stop codon and stop the protein from being made. So if we look at the previous one there, we know that UCG made serine, and so that's normal. So this would cause a problem in that strand, and you would then write that out and say, yes, okay, the protein would not be the same, and so forth. Now, what we could, there are some substitutions that would not cause a change. So let's say instead of, let's keep this as a G, and let's substitute, let's say we changed this to a G here. Okay, so this would now become U, and T, G goes to C, so U, this would be a C now, and we switch this to a G and UCC. So what does UCC produce? UCC is still serine. So if you substituted a base here, that wouldn't cause any problems, and that would keep this as serine down there. So you can see that some bases, if you substitute the third base, often it doesn't make a major change. So the bases in the third section of the codon don't really cause many problems. But in the first and second one, you do get those problems, and you saw that stop codon there. So that's how you do a substitution mutation. Now let's take a look at possibly doing another one. All right, what about a deletion or an addition mutation? Let's do an addition one. So I know it's not the same as what's up here, but let's say we insert a base right here. Let's say another G comes into here. So in this case, again, we have the A, G. Now everything slides to the right. So this C would slide over then if we inserted a G in this spot. So we now would have C, G, A, T, A. This G slides over. G, A, and this A slides over. A, C, T, and T, A, T. So you get you get a major change. So see, and obviously this is going to really alter the protein quite a bit. So if we go ahead and transcribe this, we get UCC, GCU, UAU, CUU, UGA, and AUA. So let's take a look at what that would be. UCC is still serine, so no change in that first codon, even though we inserted a base. GCU is now alanine, which I'm pretty sure is going to be different. So we'll look at that in just a second. UAU is tyrosine, TYR. CUU is leucine, LEU. And UGA is a stop. So we have a new stop here, and that would cut off that protein. So now our protein would look like this and is quite different from the original protein that is here. So that is an example of an addition mutation and how that works. Again, addition mutations cause major changes. We put that G in front of that G there and caused a lot of things to slide over and altered quite a few of your codons and obviously your amino acids. So that's how you solve problems like this. You often will have to then, just write these out in a notebook or on a piece of paper. Make sure things are lined up when you're doing these, and you'll find yourself way more successful in showing us how proteins are made and how mutations work. Hope you have a great weekend. Thank you.